thank you everyone for attending this tutorial. So my name is Mathias Jacquelin, and I'm a member of the Scalable Solvers group from the Computational Research Division. And today I'm gonna give you some feedback about how we have used UPC++ as part of our implementation of multiple sparse solvers, and the main example being the extend add operation which is used in sparse multifrontal solvers. So traditionally, I mean, sparse matrix factorization have displayed a very imbalanced communication pattern and have fairly low computational intensity. And so this causes a challenge for the communication frameworks. In this particular case, I'm going to talk about the extend add operation, which is a fundamental building block for multifrontal sparse solvers. So multifrontal algorithms are a particular type of factorization in which the sparse matrix or the factors corresponding to a sparse matrix are seen as a hierarchy of condensed matrices called frontal matrices. So on the right here, you have what we call an assembly tree of 3 frontal matrices. And basically, all you have to take away from this is that there is a parent-children relationship. Each of the sub-matrices are composed of, each of the frontal matrix is composed of 4 sub-matrices. So basically, if we look at the parent over there to the right, we have the F11 matrix, F12, and F21, which are called the factors, while the lower right matrix, the F22 matrix, is called the contribution block. So one thing that I've mentioned is that in multifrontal algorithm, we are dealing with condensed matrices. So each of the frontal matrix, each of the submatrices of the frontal matrix are actually dense matrices, but they represent a sparse matrix. So basically how this works is that if we look at the overall sparse matrix, here I'm representing the factors corresponding to the left child, which are on this block column on the left here and block row at the top. And these, as I mentioned, have a parent-children relationship with the blocks to the right here. So what's going on is that when you're actually factoring the matrix, when you're going to be done factoring these block columns to the left here, you will have to update the trailing matrix, which are the columns to the right. And because operations are sparse, you're only going to update a subset of them. So indeed, those like tiny blocks corresponds to a sparse update. However, in multifrontal algorithms, what happens is that everything is condensed like this, as basically a view from the corresponding to the update from this block of columns to the rest of the trailing matrix. And so as a result, what's going to happen is that the linear algebra or the computation part is done in dense linear algebra. However, there is one very important step, which is called the extend add operation, and I'm gonna give you more detail about that. So, in terms of computations, as I mentioned, the first step is to factor the upper left corner here. Then the F21 and F12 blocks are updated, are computed, and once we have these 2 blocks, we can we can compute the contribution block, the F22 block here. And now this F22 block needs to be sent to the parent, sent and accumulated in the parent. So this contribution block contains the updates to the parent, and that's why it needs to be accumulated. But because we are dealing with condensed matrices, basically what we have to do is to expand the entries to find their corresponding location in the parent. So if this ILC is the row indices, row and columns indices in the child, then we need to find those entries in the row indices of the parent. And so this operation is called the extend add, because what's going on, if we remember the overall view of the matrix, we are updating like these sparse entries, for instance, which are denoted by blue dots. And so these are at, sparse, I would say, locations in the parent. So one thing that the extend add operation does is to find where in the parent the blue dots need to be accumulated, and then do the sum. And so that's why the operation is called extend add, because the indices are first expanded into those of the parent, and then we add the numerical values. All right, so we have, as part of this project, we have developed various implementation of the extend add operation. And all of these implementations contain a common binning of the data into per destination contiguous buffer. And so this is, I have to stress out that this is not a requirement for the UPC++ implementation or the MPI point-to-point implementation that I will mention, but this is done here for memory access efficiency. So traditionally, in most state-of-the-art multifrontal solvers, the extend add operation is implemented using an MPI all-to-all V operation. And in order to have a complete view of the performance here, we also have implemented a point-to-point based implementation using non-blocking I-send, I-receive operation joined with either an MPI wait all or MPI wait any synchronization. And we compare these three implementations to our UPC++ implementation. So the UPC++ implementation is based on RPCs. And here the RPC is doing the extend add operation itself. So what it does is that after we are done binning the updates coming, for instance, for this pink processor in the child here, we bin them into per destination contiguous buffer. So all the entries in blue are going to the same destination, and the entries in green are going to two different locations. So we bin that data, and then we issue an RPC on each of those remote processes. And this RPC first send the contributions, so the blue dots in that case are sent to the processor in gray using a UPC++ view. So this is how the data is shipped to the remote process. And once the RPC is executed on the remote process, then the body of the RPC is comparing the index set of the child to that of the parent, and the numerical values, which are located in the UPC++ view, are then accumulated in the parent. All right. So let's take a look at the code, because we are talking about performance, but also productivity here. And so this little overview here shows the code for the extend add operation for the MPI all-to-all based variant. And on the right, we have the UPC++ code. And so as you can see here, basically the number of lines, which is one of the metrics we can look at, is the same. But don't worry, we're not gonna do a walkthrough through this chunk of code, and I'm gonna give you just a quick overview of what's going on here. So in our implementation, we have a class for each of the frontal matrix, And as you can see here, we have the 4 submatrices here. So as member of that class, so F11, F21, and so on. I'm going to walk you through the important parts here, and we're not going to do a line-by-line rundown. So the first operation we're doing, the first function I'm going to talk about is the extend add function, which is the one setting up the communication pattern, if I may say. So what's going on here is that we have basically a future on which we are going to conjoin all the remote operations. So in our case, all the remote RPCs we are going to issue are going to be conjoined into that future. And when those RPCs are going to be executed, we're gonna wait on the future. That will synchronize and wait for completion of all the RPCs. Sorry. So the RPC calls themselves are done by the EADD send operation that we are calling on both the left child and the right child. And so this function is just looping through all the target processes for which we have to send some data. And it's going to create a UPC++ view of the data using the UPCXX make view function call, corresponding to the chunk of the buffer in which we have binned the data. And then it's going to issue an RPC calling the accum function on the remote process. So this accum function is the one that's going to do the actual computation, and it's going to be executed on the remote process where the data needs to be accumulated. So here the idea is that we are basically unpacking the values in the UPCXX view using this for loop here. And then we're going to find the location and accumulate it in either F11, F21, F12, or F22 submatrices. So this is basically how the code works, and it involves like several UPC++ constructs. So we are using UPCXX teams because each of the frontal matrix involve a subset of the processes. We are also using promises. We are using distributed object, futures. So many UPC++ construct. And what I want to stress out is that this gives us, this will not hinder performance in the end. And we're going to show some performance data now. So here's the performance of our UPC++ based implementation on Cori Haswell. For the Audi KW1 matrix, which is a matrix from the Sweet sparse matrix collection. So on this plot, so this is a logarithmic scale, and we're talking about runtimes. So we want the lowest runtime as possible. And as you can see here, the UPC++ RPC-based implementation, which is displayed with the red line here, performs the best and achieves a speed up of 1.8x over MPI all-to-all-V based implementation. Interestingly, on this platform, the MPI all-to-all-V is only able to outperform the point-to-point based implementation at scale. But this shows that this, even if we are using, several, many UPC++ constructs, this shows the low overhead of the library here. And how efficient it is to schedule those to do those irregular transfers. On Cori KNL, we have a similar behavior where the UPC++ RPC implementation is achieving a speed up of 1.63x at scale over the all-to-all-V based implementation. I have to mention that here, we're talking about multifrontal factorization. So we have generated the assembly trees and frontal matrices from a state-of-the-art solver called StrumPack, which is developed here at the lab. And StrumPack is also an ECP project. So we've seen so far that UPC++ allowed us to improve the performance of the extend add operation, but everything until now were, I would say, not a full solver, only a part of a solver. So I'm going to talk about now the experience I have myself on a production solver called SIMPACK. So here we're talking about the full solver. And SIMPACK is a solver developed here in the Scalable Solvers group, and which is targeting sparse symmetric matrices. So we're not going to get into the details of the solver, but basically it has a task-based scheduling mechanism, which involves what I would refer to as a notify get mechanism. So what's going on is that, let's just say a set of columns in the matrix have been factored. So the data has been produced. That's the first step. We have some data lying around on a process. So that process, when it's done processing the task, it's going to notify all the processes, all the remote processes that are expecting that data by sending them a global pointer, a UPC++ global pointer to that data using a RPC call. When that RPC is executed on the target process, then the pointer, which has been transferred over the network, is going to be enqueued somewhere on the remote process, and the tasks which are requiring that data as an input dependence will be updated to reflect that that dependence has been, at least that the data corresponding to a dependency is available somewhere. The next step is that when all the data corresponding to the input dependencies to a task is available on remote processes, then the task is moved to a queue called data available task. And here, what's going to happen is that the scheduler will pick a task from that queue and will issue remote gets for all the incoming dependencies in order to actually transfer the data. Similarly, we are going to track the completion of those remote get operations using futures. And once the transfers are complete, then the dependency count is updated. And when all the data has been moved, then the task is moved into a list of tasks which are ready for execution. So here, as you can see, we are involving a RPC call, which corresponds to step 2, and then a one-sided remote get, remote memory access to fetch the data. So this is basically how the communications are orchestrated in SIMPACK. And now we had, I'm going to give some more details on the data distribution here, because originally SIMPACK was using a 1D data distribution, which is very nice because it balances the number of flops, the number of non-zeros, which correspond to the memory usage. And that's easy to do with sparse matrices with a 1D distribution. However, it lacked strong scalability. And so we have a work in progress where we have introduced a new 2-dimensional data distribution where we do the load balancing in an explicit way. We're not using a regular block cyclic mapping. And basically, we are able to balance the number of non-zero per process in a better way, balance the computational load. But what it results in is that we get a finer granularity task graph. And this is important because the overheads, which are very low with the UPC++ library, do allow, the fact that UPC++ has low overheads allow us to fully exploit the finer granularity of the task graph in order to achieve, in the end, a better, strong scalability. So on the right here, we have two experiments which have been run on Corey Haswell. So Serena is a matrix also from the from a Sweet sparse matrix collection. And we see for that particular example that at scale, we achieve a speed up of up to 3x over the 1D data distribution. For this other example, which is a matrix coming from the electronic structure computation, from an electronic structure computation application, the speed up achieved is 2.5x. So we do achieve excellent performance at scale on a full solver using UPC++. And now how this stacks up against state-of-the-art solvers. So here we're comparing the performance of SIMPAC against the performance of PASTIX, which is a solver for symmetric matrices. And for the FLAN 1565 matrix on Corey Haswell, we see that so the 1D data distribution was already slightly outperforming PASTIX here. But the new 2D data distribution achieved a speed up of 1.8x, which is excellent here. For the Audi KW1 matrix, we have a similar, if not better, trend, where the maximum speed up is 2.13x. So throughout this presentation, we've been able to see that UPC++ through various constructs such as RPCs allowed the implementation of I would say complex communication patterns, such as this notify get system that is being used in the scheduler of SIMPAC. SIMPAC being a full solver, it has to interoperate with MPI, and UPC++ allows to do that. Through the non-blocking API that is exposed by UPC++, we've been able to achieve excellent performance by better overlapping communication with computation. And we've been able to increase the efficiency of the extend add operation, and also in the case of SIMPAC, outperform state-of-the-art sparse symmetric solver. So I thank you all for your attention, and I'd be happy to take any questions.
This link here contains the slides. Among them is contact information for us on the first page.